Okay, so in previous lecture we have seen the static and dynamic equalization circuit for equalize the voltage, right, in series connection of SCR. Clear? Now I will repeat. For calculation of C, delta Q was the uh, let me remind those things that delta Q was proportional to product of current and time, and it is the difference in reverse recovery charges of 2 SCR. The voltage induced by delta Q in the capacitor connected across thyristor T1 would be delta Q by C, where no voltage induced by delta Q. Delta Q is what? That is Q2 minus Q1 in C connected across thyristor to T2, because during that time T2 was conducting, right? So there is a voltage difference of delta Q by C, to which two shunt capacitors are charged. I hope you remember all this thing. Now T1 share highest transient voltage, let us say it is VBM. Therefore T2 would have VBM minus delta Q by C, where delta Q is the charge difference, charge accumulation difference between these two capacitor, right? So string efficiency is V1 plus V2, which is equal to VBM plus VBM minus delta Q by C. On the basis of this, we can calculate voltage V2 is equal to half Vs minus delta Q by C. Now let us say if we consider that there are n SCR, so the transient voltage across thyristor 1 is VBM, and remaining SCR would have VBM minus delta Q by C. So the total voltage Vs is equal to V1 plus n minus 1 times voltage V2. V2 is the voltage shared by the remaining SCR. So it is come out to be VBM plus n minus 1 VBM minus delta Q by C. On the basis of this, we can calculate capacitor C is equal to n minus 1 delta Q upon n VBM minus Vs. Similarly, we can calculate voltage V2, which is equal to VBM minus delta Q by C. Right? Now we will start our today's topic, that is the parallel operation. Parallel operation of thyristor we carried when there is high current rating is required. So T1 and T2 are connected in parallel, they will share equal voltage Vt, and their current is I1 and I2, right? Their characteristic is drawn in figure. You can see for the same voltage Vt, thyristor 1 is sharing more current I1, right, whereas thyristor 2 is sharing current I2. You know, as the current sharing by any thyristor is increased, it heated fast. At the same time, its dynamic resistance is also going to decrease, so it will start further more current. Now this further more current further heat up this thyristor, and finally it may burn, which you can see in the next characteristic, that the thyristor 1 dynamic characteristic is improve. Improve means it is now dia by dvt. You can notice that for the same voltage it is having more current. So in that way this will start carrying more and more current, and it may burn. String efficiency is same as we have already defined for voltage, that is I1 plus I2 divided by 2I1. So it is again for the parallel connection also, it cannot be more than unity, right? So this is you can say we have to have something which prevents flow of current in such a fashion that it may burn, should be stopped, right? It should be stopped. So for an SCR, thyristor T1 has longer turn on time, let us assume. So as compared to remaining n minus 1 SCR, so T1 is subjected to low forward voltage, and it may be possible it may not turn on if this voltage is less than the finger voltage. Just imagine the situation. Let us say T1 has longer turn on time, so it will turn on after other, let us say there are two thyristors T1 and T2. T2 is having less turn on time and T1 is having longer turn on time, so T2 get turn on. The moment T2 get turn on, it will make the thyristor T1 in reverse bias, or means not in reverse bias exactly, means the small voltage would appear across thyristor T1 because both are in parallel. So if this voltage is less than the finger voltage, it may be possible this T1 is not turn on, right? So that we must under that situation we must understand, right? So the remaining SCR means that the thyristor T2 and all, they will get heated. Why? Because T1 is sharing less current and T2 is sharing more current. Their dynamic characteristic is also decreases. Once the dynamic characteristic decreases, dynamic resistance is decreases. So more and more current will flow through those SCR which are already turned on, right? And finally what happen, your thyristor may get burned on. So they should not be heat up. What we have to do, we have to design heat sink in such a way that heat distribution is uniform. So if you see this type of heat sink, this article we have also already covered when we have discussing that high di by dt, right? Anyhow, so this heat sink has to be in circular way, and each devices, if there are three phases, they have to be at equilateral angle, right? There the device has to be mounted at like this here, means at the equilateral triangle, so heat is equally distributed, right? Another way is you just connect one interface reactor, this interface reactor. So we know according to Lenz's law, current opposes the reason why, because of which it produces, right? So if we assume that I2 is high, the moment I2 is high, this inductor polarity would be in such a way that it would oppose the flow of current, right? So it would oppose the flow of current. Here in this figure, the value of current I1 is high as compared to I2. So when I1 is high, inductor would oppose this. So because of this, the polarity would be like this, and it will try to decrease I1. At the same time, the polarity of this side is minus and here it is plus, so it will try to increase this I2. So I1 is decreasing, which was high, it was decreasing. I2 which was low, it was increasing. So ultimately they will try to balance I1 and I2. So interface reactor is used there to balancing this I1 and I2 current, right? So whenever we have this parallel combination of thyristor, we have to have use, first thing, the heat sink, proper design heat sink, so that heat is distributed equally evenly and other thing, we must use the interface reactor, right? Okay, now we will do some numerical based on this. Suppose we have available thyristor of 1 kV and 200 ampere. Now we have to design a string which can handle 6 kilovolt and 1 kilo ampere current, and the derating factor is, we have two cases, one in one cases it is 0.1, other one is 0.2, right? This is very simple question, you just try to solve this. When I'll join university, hopefully on 30th, then we will again do these numericals in class, right? And this is very very simple and formula based numerical, don't get panic, right? You already know drf is equal to 1 minus string efficiency. So for series as well as parallel, the formula is same, you just calculate, and you can find out how many thyristor could be connected in series and in parallel to get the string efficiency as desired by the problem, right? With this I end the lecture, and I hope by Monday I'll join, then we will carry on in regular class, right? Bye bye, take care.